let's pick up where we left off next time. Today, we're going to actually finish the first part of the course. We're going to finish analysis of the continuous time linear systems in time domain. Now, we already covered the zero input conditions, zero input response. We already covered zero state response. So we're going to put two of them together to get a total response, and that's what we're going to be doing today. Now, next time when we come, that would be on Thursday, we're going to have a review class. So I'm going to spend the whole class doing nothing but problems. I have prepared some problems that I'm going to go through, but I would like you also to, you've been assigned quite a bit of homework. So let's play Stump the Instructor, see if you can dig a problem that I cannot solve. So let's see out of those problems, if you find out something that you couldn't solve or that you're confused about, let's get those out of the, and I'll try to solve them here. You'll still have a copy of the ones that I solved posted on the web, so that gives you another set of problems so that you can practice. And then after that, we're going to close this section and move into discrete time systems and pretty much do the same analysis as we did for continuous time, but now discrete time systems. Okay, so let's talk about total response of the linear system. So here's the setting. We have our linear system that I call S. This system has some energy stored, so there are some initial conditions in it. And it's excited with the input x of t, and it's producing output y of t. It has some, it is described with differential equation. Q of d times y of t is the same as P of d operating on x of t, where P and Q are the operators, right? The polynomial that is the function of d. And we know that the output of the system y of t is going to consist of the two components. One is going to be zero state response, y, zs of t, and y, zi of t. Zero state response is the response to the x of t, assuming that the initial conditions were zero, the system was relaxed. And zi of t is the zero input, meaning response to the initial conditions alone. And then sum of the two will give us the total response of the system. So we already have all the pieces. So let me summarize everything in a process that you need to follow. And I kind of have 4 steps here. And I'll give you those 4 steps, and then we'll spend some time working through a couple of examples to show you how you actually execute those 4 steps. So if you were to determine the output of the linear system to a particular input x of t, here's, and you're given the initial conditions and you're given the differential equation, here are the steps. First one is determine the form of y, zi of t. That's determine what the fundamental modes of this system will look like. We first determine this one, but you leave the constants here, because usually the initial conditions are given with this x of t, right? So we're going to get rid of them at the very last step of this approach. The second step is determine impulse response. H of t. We've seen that we determine impulse response by looking at the response of the companion system and then taking the derivative of that response. Bulk of the work that is required to determine H of t is already done in the step 1. So we leverage on that in a step 2. Then 3, we determine zero state response as y, Zs of t is equal to h of t convolved with x of t. So this is our zero state response. And in the fourth step, we're going to satisfy initial conditions. So eliminate the constants and satisfy initial, eliminate the constants in y zi of t using initial conditions. Okay? So that's a general process. As I mentioned earlier, this is assuming that the initial conditions are given at 0 plus, in which case you actually have to eliminate the constants in this step. If the initial conditions are given in 0 minus, then really this is just, you would determine them from this. You can determine them in this step because this was before the actual input came in. So, you know, they need to be satisfied at 0 minus. So that will depend from problem to problem. So let me work an example. So this is example 2.10 in your book. And we are considering the following system. We are considering the system d squared plus 3d plus 2 operating on y of t is the same as dx of t. X of t, our input, is given as t squared plus 5t plus 3. And our initial conditions is our y of 0 plus is equal to 2 and y dot of 0 plus is equal to 3. So we have everything we need. So let's just go through these 4 steps and see how do we get the result. In the first step, we are solving for the form of the zero input response. To do that, we form our characteristic polynomial, q of lambda, which in our case becomes lambda squared plus 3 lambda plus 2. And we solve for this factorizes easily as lambda plus 2 times lambda plus 1. So from here, lambda 1 is equal to minus 1, and lambda 2 is equal to minus 2. So we get the form of our zero input response as some constant C1, e to the minus 1 times t, plus C2, e to the minus 2 times t. That's our zero input response of the system. It has 2 undetermined constants, C1 and C2, that we'll have to find in the last step. It consists of 2 characteristic modes, where each one of the modes corresponds to this characteristic value. In this case, there are 2 real distinct values, therefore we have 2 exponentials as outputs. Okay, so that's the first step. The second step, we're looking to the impulse response. Well, impulse response, we saw that was given as B0 times delta of t plus P of d, y n of t, times u of t. That was a general form of the impulse response of a linear system. B0 is the coefficient on the right hand side, the highest, the nth order coefficient in a P of t. In this case, B0 is equal to 0. So the system does not have the output, or the impulse response doesn't have delta pulses. T. And then this, so therefore we're going to obtain h of t as differentiating yn of t. Yn of t is obtained as zero input response for a separate, special initial conditions, right? To obtain, go ahead.
I got lost on the B0, how you got 0.
B0, remember, B0, what is B0? You remember what B0 is? This is our polynomial. QOD times Y of t is POD times operating on X of t. General form of this equation is this: d to the power of n plus a1 d to the n minus 1 plus and so on plus an operating on y of t is equal to b0 d to the n plus b1 d to the n minus 1 plus and so on plus bn operating on x of t. Okay? So, if this is P, this is Q of d, and this is operating on y of t, and this is P of d operating on x of t. Okay? Order of Q of d, we refer to that as n. Order of P of d, we refer to that as m, right? So usually these polynomials are of different order, where the most common case is that the P of d is of the lower order than Q of d, meaning that there are a couple of terms here which are zero. So if you compare this here with this, you can see that in this case n is equal to what? In our case, in this case,
And it's 2.
n is equal to 2, and n is equal to 1. So b0 is equal to 0, right? In a derivation of this formula, we explain why we have this impulse here, right? And we explain that b0 has to be what is here, right? So since b0 is equal to 0, we know that our impulse does not have, impulse response does not have impulse terms, right? So b0 is equal to 0, just observing what those polynomials are. So all we need to do is determine this. Well, first, what is yn of t? Yn of t was an impulse response of the companion system. Companion system is the one that has the same differential equation, but doesn't have d here. It just has 1 times x of t. Go ahead.
But how can we make sense of this if we say that the impulse response does not have an impulse?
Okay. Impulse response is, let me give you an example so you can see right away what we're talking about. Let's say you have a circuit or just a block diagram that does this, minus infinity to t, dt. So what is this? This is an integrate, right? It will integrate. So here, y of t is equal to integral from minus infinity to t, x of t, dt. If I differentiate both sides, then I get that dy of t is equal to x of t. So that's a differential equation that describes this system, right? So what happens when I present an impulse to the system? What is the response? So let's say my x of t is delta of t. Let me just do it graphically. This is t, this is x of t, right? Occurs at 0. So what is my y of t? Y of t is an integral. Is an integral from minus infinity to t, x of tau d tau, right? At any given t, y is whatever I managed to integrate up to that point. So how does my y look like? It is 0 all the way up to 0. What is it after 0? Well, it's an integral under the curve of this one. What's an integral under delta? 1. So this one continues like this. Right? So this is y of t. So you see that this one has an input, has an impulse, but the output does not. right? Output never goes to infinity. So you don't have to have an impulse to in the output if you have an impulse in an input.
Yeah, but this one up here is saying we didn't have an impulse on the input.
This one we have impulse on input.
No, the one on the left, the B0 equals 0.
Yeah, here we say this is an impulse response. So the impulse response of this system is just like the impulse response of this one. When presented with a delta pulse at the input, it will not have delta pulses in the output. It will have some step functions or possibly something that is discontinuous, but it will not go to delta. It will not go to infinity. Right? Right? You have some systems which have low inertia, right? And that means they almost connect input and output. And when you hit those when impulses, you're going to get impulses in the output. Even more than that, you can get derivatives of an impulse, right? If this was a differentiator, in the differentiator, let me change the. In a differentiator, you would have something like this. This would be the, or let's say just a simple system. Let's say this is the simplest system at all. X of t, y of t, and then y of t is equal to a times x of t, right? So here, differentially, if you want to differentiate, just if you care, but you don't have to. Both of the p and q and p are of the order 0, right? So there, if I hit the system with an impulse, what do I get at the output? I get the impulse as well, right? So this is an example of a system where the order of the operator of the polynomial on the left is the same as the order on the right. Therefore, B0 here is equal to A, and your impulse response is going to have impulses in it. But if the order of the polynomial here, order of Q, is larger than order of P, then the system does not have impulses in its response, right? If you present it with an impulse at the input, it will not result in impulse in the response. Usually it results in some discontinuity. Something jumps a little bit or changes by step, but never goes to infinity, right? So that's our case here. Now, what we showed a couple lectures ago is this, that this Yn of t, which is the impulse response of the companion system. Companion system is the system that is created from this one by actually setting p of d to be 1. It has the same q of d, but has a different p of d. P of d is equal to 1. And we show that this Yn of t is going to have the same form. So it's going to be c1 e to the minus t plus c2 e to the minus 3t. But it will have different, 2t, but will have different conditions. Yn of 0 is going to be 0, and Yn dot of 0 is going to be 1. If this was a higher order, then all the derivatives up to the nth derivative, actually n minus 1 derivative, will be equal to n minus 2 derivative will be equal to 0, and n minus first derivative will be equal to 1. So we get exactly n equations here where we can solve for these n coefficients. So if I substitute these two in here, I get that C1 plus C2 has to be equal to 0. And then minus C1 minus 2C2 has to be equal to 1. So if I add these two, I get that minus C2 is equal to 1. C2 is equal to minus 1. And C1 has to be equal to 1. So my impulse response of the companion system is going to be e to the minus t minus e to the minus 2t, for t greater than 0. And now my impulse response, I'm going to obtain by applying p of d to this impulse response of the companion system. So let's say this is step 1. Step 2, we're going to get h of t as p of d applied on yn of t times u of t. So in our case, p of d is given as just a d, right? So it would be a derivative of this one. So it becomes minus t plus, minus e to the minus t plus 2 e to the minus 2t times u of t. So that's the impulse response of this system. Okay, let me double check because I'm been known to make mistakes, right? So it's correct. So did you follow this step? This is a most generic formula. This applies always when n is smaller or equal to n. So in our case, n is smaller than n, so b0 is equal to 0. You go here, you say, okay, in that case, the impulse response of the companion system has the same form as a zero input response of the system itself. I have these initial conditions, which are always the same, right? Then I use them to solve for the constants, and this is the impulse response of the companion system. The impulse response of the system itself I get by differentiating with p of d on the impulse response of the companion system. So I get h of t. And that's the end of the step 2. In the step 3, we have to convolve this with whatever I have for the input. So let's do that part. So step 3 is zero state response. We're saying that y, zero state of t, is equal to x of t convolved with our impulse response h of t. In this case, I'm going to write this as integral when tau goes from minus infinity to plus infinity, x of tau times h of t minus tau d tau, right? So let's substitute what they are. X of t is given, or was given, and now erased. So it was integral when tau goes from minus infinity to plus infinity, and then I have tau squared plus 5 tau plus 3. And it's important to put these, u of tau. Why is it important? Because we have to make sure that we interpret this correctly. This x didn't exist before 0, right? So this is the value, this is the function, but only for positive taus, right? So that needs to be put into integral. Now h of t, I erased it, but let's say remember, h of t has the similar thing there. It was given as minus e to the minus t plus 2 e to the minus 2t times u of t. This is also a function of time that exists only for positive t. Now you can see this, this has a discontinuity at 0, right? When t is equal to 0, what you hit impulse, what comes at the output at t equal to 0, this has a value 1, right? So the response of the system was 0 before the impulse came in, but then it jumped from 0 to 1 as a result of an impulse. It has a discontinuity. It's just it didn't go to infinity because b0 is equal to 0. So now we substitute that in here, but we have to, instead of t, we have to put t minus tau. So this becomes minus e minus t minus tau plus 2 e to the minus 2 t minus tau. And then the, oh, sorry, see, I say it and then I preach, but I don't practice. So u of t minus tau d tau. Okay? So now we have to, once you write this, then you have to use these guys to your advantage. How do we use them to our advantage? We say y0 state of t. Now, when t is smaller, tau is smaller than 0, you can see that this guy becomes 0. So there's no need to integrate for any tau that is smaller than 0. So that's always going to limit your lower boundary. Tau is going to go from 0, because from minus infinity to 0, this is equal to 0, and there is the whole subintegral function is equal to 0. Now, for tau greater than t, you can see that the argument of this becomes negative. Therefore, the subintegral function becomes 0 as well. So there's no need to integrate anywhere past tau equal to t, right? Now that this one and this one operated, then you just put this in here. So it becomes tau squared plus 5 tau plus 3. And this point you can get rid of u's because they are 1. In this interval that you're integrating, they're both equal to 1. So no need to put them in there. And then you can say minus e to the minus t minus tau plus 2e to the minus 2 of t minus tau, and then tau. Okay? Now that you get this, you can see that this is a function of t. There are some terms there that are only t terms that can come out. So let me bring those out and then just leave the terms that depend on tau inside the integral. So you end up y0 state of t is equal. You can see the first integral. I can take e to the minus t outside, and then this minus minus gives me plus. So this becomes minus integral when tau goes from 0 to t, tau squared plus 5 tau plus 3 e to the tau, and then everything multiplying e to the minus t. And then the second integral has plus, I can put 2, integral from 0 to t, tau squared plus 5 tau plus 3 e to the, again, minus 2 times minus tau is 2 tau, and then d tau, and there's a d tau here. D tau here. There's d tau there, and then this multiplying e to the minus 2t. Okay? So these are the two integrals. And let me rewrite this in saying that this is minus I1 of t, e to the minus t, plus 2 I2 of t, e to the minus 2t, where I1 of t is this integral, is tau goes from 0 to t, tau squared plus 5 tau plus 3, e to the tau d tau, and then I2 of t is this integral, 0 to t, tau squared plus 5 tau plus 3, e to the 2 tau d tau. So we need to solve for these two integrals. Now, recall this. This is somewhere in the calculus book that says an integral from a to b, e to the x times e to the ax dx is equal to x over a minus 1 over a squared e to the ax from all right, so let me not do this. Let me call this alpha. So it's different. Alpha, sorry about it, alpha squared a to b, because I have a and b in both cases, right? So that's if you integrate the first order. If you integrate from a to b second order, alpha x dx. Then this ends up being x squared over alpha minus 2x over alpha squared plus 2 over alpha cubed e to the alpha x from a to b. All right, so those are two table integrals that we're going to utilize in this case. Knowing these two, then I can evaluate I1 and I2. So I1 ends up being, let's see, the first one, I have tau squared e to the tau d tau. So it's this guy here, but alpha is equal to 1. So I'm going to have tau squared over 1 minus 2 tau over 1 plus 2 over 1. So it's going to be tau squared minus 2 tau plus 1 from this term here, plus 5 times tau minus 1, and then plus 3, everything multiplying e to the tau from 0 to t. And then you can see here when you substitute t here, you get t squared. So this is equal to t squared. I have minus 2t plus 5t. This is going to be plus 3t. And then I have 1. No, this should be 2, right?
Yeah.
Yeah, 2. All right. 2. Then 2 plus 3 minus 5 is equal to 0. So tau squared plus 3 e to the t. So that's the first integral. And then I2 of t is kind of using the same formulas, but now your alpha is equal to 2. So this ends up being tau squared over alpha, which is 2, minus 2 tau over alpha squared, which is 4, plus 2 over alpha cubed, which is 8, plus 5 times, tau over alpha, so it's going to be tau over 2, minus 1 over alpha squared, which is 1 over 4, and then everything multiplied by e to tau, evaluated from 0 to t. So when the smoke clears here, this is t squared over 2 plus 2t plus 1/2 e to the 2t minus 1 over 2. So that's the second integral. Now we need to plug that in here and get the zero state response. Y zs of t ends up being minus t squared plus 3t. Now an interesting thing is, you see, I have e to the minus t multiplying this. So e to the minus t cancels with this et. So I have just minus e1, which is minus I1, which is t squared plus 3t, with minus up front. Then I have plus 2 times I2, which is this guy. But you can see that there is e to the minus 2t will cancel with this e to the 2t. So I'm going to have just 2t squared over 2 plus 2t plus 1/2. And then I'm going to have minus e to the minus 2t, because 1/2 times this 2 is 1, and then e to the minus 2t. So this is my zero state response. Obviously, this can be cleaned up a little bit. You have minus t squared plus 2t squared over 2, which is t squared and t squared cancel. So these two will cancel. You have 3t here. You have 2 times 2, which is 4, minus 3 is t. And then you have plus 1. And then, so just t plus 1 minus e to the minus 2t. So this is our zero state response. for t greater or equal to 0. Okay?
Excuse me, sir.
Uh-huh.
To solve for the integration, can we use integration by parts?
Can we use what?
Integration by parts.
Yeah, yeah. In this case, that's what you would do, is that I kind of cut the corner here using these two integrals. This is obtained by integration by parts. If you do this one, integration by parts, you get this general formula. So I'm just applying this general formula to this one, right? But you would have to do it twice, right? Because it's a second order polynomial, so you have to integrate twice by parts. But other than that, yeah, of course. Now that we have zero state and we have a zero input, our total response, so this is where now to this in the step 4. So in step 4, we say our total response is going to be our zero input of t plus our zero state of t. We have our zero input as c1 e to the minus t plus c2 e to the minus 2t. And we just obtained our zero state to be plus t plus 1 minus e to the minus 2t. So that's our total response in this case. We also have initial conditions. Y total at 0 was given at the very beginning to be 2. And Y total prime at 0 was given as 3. So let's substitute that here. From the first equation, you get C1 plus C2 plus 1 minus 1 is equal to 2, right? Or t equal to 0. And then if I take the derivative of this, I get minus C1 minus 2C2 plus 1 minus 2 is equal to 3. I did everything correct. 1 minus, okay. I don't know, let's see. So this cancels, so C1 plus C2 is equal to 2, and then C1 minus 2C2 is equal to, well, this is minus 1, so it's 1, and this is minus 3, so minus 4, right? Am I correct? No. Oh, you see where I made a mistake. When you take the derivative, minus 2 comes down here, it becomes plus, right? So this conveniently cancels, and I get that this is equal to 0. Okay, do you see where I made a mistake? When you take the derivative of this is minus C1. When t is equal to 0, this is 1. And you have minus C2, and then plus 1 from here. Derivative of this is 0, and derivative of this is 0 is 2. Right, so
it should be C1 plus C2, not C1 minus 2C2.
C1 plus 2C2?
Yeah, C1.
no, why?
Yeah, it's correct.
Oh, here.
Yes.
They're a step ahead of us. I just corrected this one.
Yeah.
It takes me a little bit to correct the other, right? So from here, if I let's say subtract first one from the second one, you get that the C2 is equal to minus 2, and C1 has to be equal to 2. No?
C2 is equal to plus 2.
2C2 minus C2
Yeah.
is going to be equal to minus 2.
4.
Minus
4.
C1 is 4.
C1
4.
is equal to 4.
Minus C2 is equal to negative 2.
No. 2C2 minus C2.
C2 is equal to minus 2, yeah.
C2 is equal to minus 2, and
Yeah.
C1 is equal to
to 4.
4.
Yeah, that's good.
Yeah, so C1, so 4 minus 2 is 2, and then 4 plus 2 times minus 2 is equal to 0. Right. So these are the constants, and we finally get y t of t equal to C1, so this is e to the minus t, plus C2, which is 4, e to the minus t, minus 2 e to the minus 2t, plus t plus 1, and minus e to the minus 2t. So we get 4 e to the minus t, minus 3 e to the minus 2t, plus c plus 1. And then this is true for t greater than c. Now, what you're going to find out in outputs, it's always this. You're going to have this part, and you're going to have this part. These parts are your transients. They're the ones that consist of the modes of your system, right? The system had two modes, one at e to the minus t and the other one at e to the minus 2t, right? And these transients are the ones that are going to eventually die in every stable system. Why? Because every stable system has, otherwise, if it doesn't, then the system is unstable. In all stable systems, these transients, the characteristic modes, are dying exponentials. And then you have this one here, which kind of resembles your input. Your input is a polynomial, so your output is also a polynomial, right? But in some books, you will find these to be called transient response and the forced response, right, or steady state response. And the steady state, after time becomes large, then the transients kind of die, and all you end up with is your steady state response, which is what you have on the right-hand side. Okay. I guess in your book they call this natural response. And this is forced response. Some other books would call this transients and call this steady state. Okay? So that's how one full analysis would look like, right? It's not difficult. You are actually executing these 4 steps. But I have to admit, it can be messy, right? At every step here, there are plenty of places to make a mistake. There's, to my knowledge, no other cure to that, but just to work a lot of problems and get proficient. Go ahead.
Considering the example, would you require us to manually solve the simultaneous equations and cross-reference the
Of course, that's the whole point. Right? It's not going to be this complicated, maybe. You know, what was complicated here? X of t was pretty long. It was a 2-degree polynomial. So when you convolve that with a bunch of exponential, you ended up with something that was long. If I gave you x of t was equal, for example, just u of t, then this becomes a much easier problem to solve. Right? You know, it just depends on the input. Right? But what I would like to, for you to know in the exams is I want to see these 4 steps, right? And kind of following this methodology, right? Because it's important to kind of execute them in order and properly, right? And of course, what I do is, I'll give you a secret. What I do is I make the problems, and then I make sure that every one of them is solvable within 15 minutes. Right? So they need to fit. They need to exercise the material from what we covered, but they also have to be analytically trackable. I cannot give you something that will consume a lot of time.
So like no calculators and stuff?
Hmm?
No calculators and stuff?
No calculus?
Calculator.
How would calculator help you here?
So you can solve the simultaneous equations and the calculation groups as well.
All right, well, I don't know. If you mean like a symbolic map, yeah, bring those. Those are useful. All right, so total response So that's kind of pretty much the end of this. I'm going to look at some special cases of significance to us. I already discussed it briefly last time, and this is the special significance of this exponential function. So let's take a look at what happens when I present exponential input to my linear time invariant system. So total response of linear time invariant system to exponential units. So here's what I have. I have a system. There's an input x of t. There's an output y of t. And the differential equation that describes the system, q of v times applied to y of t is equal to p of v operating on x of t. But in our case here, x is a special input. X of t is e to the st, where this s is our complex string list. Can be real, can be purely imaginary, or can be combination of both. Now, what we've learned from this example, and in general, the total response is going to be consisting of zero state response and zero input response. But it will have a form that is somewhat like this. Sum, when k goes from 1 through n, actually j goes from 1 to n, kj, some constants, e to the lambda j d, plus h of s times e to the st. Where is this coming from? We discussed last time that, I should say maybe the other way around, zero state and zero input, zero state. Zero input response consists of a whole bunch of characteristic modes. We've learned that that's always the case. Right? If the system is responding to initial conditions, it has no choice but just to produce an output that is a linear combination of characteristic modes. What we learned last time is that if you have zero state and you present the exponential, the output of the linear system is also exponential, multiplied by some constant, which we denoted here as h of s. So exponential is a special kind of function. When you present exponential to a linear system, what comes out with is pure exponential. Now, in a lot of times, in our practice, what we realize is that, especially if the linear system needs to operate for a longer period of time, and it's stable, then these things here would die, right? These transients would die. Typical example of this is, let's say, a circuit that processes AC signals. Let's say you present an AC signal to a circuit. You turn the circuit on. Initially, there's all sorts of transients happening, but eventually, at every single node, you're going to get something that is a sine or a cosine, right? It will look periodic as if these transients never existed. We're talking about a steady state response in that case. If you look at this, this is what we're talking about. These are the natural responses, transients, they will die away, and then what is left is your forced response or steady state response. The steady state response to exponential is special because you've seen in the previous example, we had a second order polynomial, and we got a steady state that's not the same kind of polynomial, right? It's slightly different. Here, if you have exponential e to the st, what we proved the last time your steady state response is going to be the same exponential scaled by a constant, right? Potentially complex constant. This h of s is, as I said, constant for any given s. For any given s. And it's referred to as transfer function. Transfer function can be evaluated h of s is p of s over p of s for some s. So if I know the s, I can plug it into this equation here, obtain what the constant is, and immediately I know what the steady state response of my linear system is, which is tremendous value, right? I know you've seen what it takes to obtain the output to any given system. I have to go through all of these steps, right? If my input happens to be a exponential of some sort, then I know immediately what the steady state response is without going through any evaluation of the differential equations. So let me give you some special cases. Let's look at the case 1. S is equal to 0. In this case, x of t, which is some constant, let me put c e to the st, is just constant, right? So I can see constant as a special exponential with a complex frequency equal to 0, right? Constant is a derivative of what? Exponential, right? Just a complex frequency ends up being 0. So if I have a constant, then immediately I have a total response of the system as a sum over j goes from 1 to n, kj, e to the lambda j t. These are all my transients, plus h of 0 times c. Okay? And in the stable system, these guys are going to die. So as t goes to infinity, yt of t is going to be h of 0 times c. So response of the linear system to a constant is a constant, right? Eventually, at the output, you're going to have a constant. So that's a easy example here. So let's take a look at a couple more special cases. Special case 2, S is equal to j omega. So in this case, x of t is equal to e to the j omega t. Right? So I have essentially complex, purely imaginary complex frequency, and my input is this e to the j omega t. So here I get my total output of t is going to consist of all the transients. J goes from 1 to n, kj e to the lambda j t plus h of evaluated j omega e to the j omega t. Just like in the previous example, as t goes to infinity, yt of t becomes h of j omega e to the j omega t. All right, so this is this special case, and this h of j omega is a complex number, right? So as such, it can be written as h of j omega magnitude e to the angle of h of j omega with j up front e to the j omega t. So I can write this as h of j omega magnitude e to the j omega t plus the angle of h of j. So what can linear system do to this e to the j omega t? It will change its magnitude and it will add to its phase, right? And now, finally, let's look at the special case 3, which is of highest importance to us. H of t, in this case, is cosine omega t. Now, as you know, this can be written as 1/2 e to the j omega t plus e to the minus j omega t. Now, you can see right away that this x of t is now a linear combination of terms like this, right? It consists of essentially term like this where I have plus j omega and another term that is minus j omega. So if I now look at the steady state response, meaning the total response of the system as for after a long time, I get that y as s of t has to be equal to 1/2. Now look at this thing here. It will have to be h of j omega magnitude e to the j omega t plus angle of h of j omega. This is in parentheses now. Okay, so that's the first one. And then plus 1/2 h of minus j omega magnitude e to the minus j omega t plus angle of h of, well, I should say minus j. So that's one way of writing it. Another way to write this is you can say YSS of t is going to be equal to 1/2 h of j omega e to the j omega t plus h of minus j omega e to the minus j omega t. Now what you realize is both of these are complex numbers on its own. If I call this z, then what is this? This is a z complex conjugate, right? Now, if I take sum of z and its complex conjugate, what do I get? If z is written as x plus jy, then complex conjugate is x minus jy. So sum these two. You get 2x. So you get the two real parts of this. So this is equal to 1/2 times 2. So just the real part of h of j omega e to the j omega t. So that's a steady state response. Now, this I can write as the real part of h of j omega magnitude e to the j omega t plus angle of h of j omega. Where is this coming from? Well, it's coming from here, right? This is, this here is equal to that, and it's equal to that, so this is what I wrote to it. But now, this last term can be rewritten once more. And I can, this h of j omega is just a constant, positive, real constant, so it can come outside. So our y steady state of t is equal to magnitude of h of j omega. And then the real part operating on e to the j omega t plus angle of h of j omega. Now if I apply the Euler's identity to this, this is h of j omega. And this thing here is the real part. I can write this as a cosine omega t plus the angle of h of j omega plus j sine of omega t plus the angle of h of j omega. Right? What did I do? I realized that this is e to the j theta, so this is cosine theta plus j sine theta. And what is the real part of this? What is the real part of these two?
It's cosine.
Just the cosine, right? So you end up with h of j omega times cosine omega t plus angle of h of j. Right? So we have a beautiful result. If I have a linear system that comes with some p of t and q of t, and then I present to that system x of t cosine omega t, what comes at the output system, y ss of t, after some time, right? Not initially, not within the first, for small t, but as t becomes larger, we reach the steady state. The steady state is going to be the magnitude of h of j omega times the cosine of the same frequency omega t plus the angle of h of j omega. What is this h? H of j omega is formed as p of j omega divided by q of j omega. So for every given j omega, I can plug that into these two polynomials, get a single number. The single number will have the magnitude at the face. The magnitude will multiply the magnitude of this cosine, and phase will add to the phase of the cosine. So this is the result that I kind of promised to you, and this is how beautiful it is to work with the cosines in linear systems, right? When you have trigonometric functions in a linear system. When I present cosine to a linear system, what comes out is the cosine. I don't have to do any differential equation. I don't worry about the shape of the output. I know exactly, I can write it out. All I'm worried about is what is the magnitude and what is the phase. And if I'm given P and Q, then I can determine this to simple evaluation of all this ratio here. I substitute my j omega into P, substitute j omega into Q. I'm going to get two complex numbers. I divide the two, and I get one complex number. The magnitude of that number is going to multiply the magnitude of the cosine. The angle of that number will add to the angle of the cosine. So all that the linear system will do to a cosine is scale it and possibly phase shift. So let's look at some examples. Some examples of the use. I'm going to stop here. So, first example, consider a system that is given with the following differential equation. D squared plus 3d plus 2 applied to y of t is going to be equal to dx of t. And let's say I had initial conditions, y of 0 is 2 and y dot of 0 is 3. You recognize this system, that's the same one we just did. And let's take a look at A part that assumes that x of t is equal to 10 e to the minus 3t. Then the question is, how does the output of this system look like? Well, I know that total output is going to consist of natural modes, and it's going to be y, what is forced, so phi of t. or it's going to consist of the transients, and it's going to consist of a steady state part. The natural modes. I know that the format of Yn of t is going to be sum over j, 1 through n, kj e to the lambda j t. That's the format of the natural modes. Now, how do I get the lambdas? I have to solve my characteristic equation. So the characteristic equation here is q of lambda is equal to lambda squared plus 3 lambda plus 2. And you remember we solved it earlier. Lambda 1 is minus 1. Lambda 2 is minus 2. Okay? So I get the format of my natural response. Yn of t is going to be some k1 e to the minus t plus k2 e to the minus 3t. So I'm done with this part. How about my forced response? Or steady state. I know in general case that y steady state of t, if the input is exponential, is going to be h of s times e to the s t. Now, what is h of s in this case? H of s is p of s divided by q of s. So in our case, p of s is d, so it's s over s squared plus 3s plus 2. Okay, so this is our h of s. So to get our y phi of t, I have to evaluate this at the complex frequency of the input. What is the complex frequency of the input? It's minus 3. So in our case here, s is equal to minus 3, and then h of s becomes minus 3 over minus 3 squared plus 3 times minus 3 plus 2, which gives us a value of minus 3 over 2. So our forced, so our steady state, or our y f of t, is going to be 10 times minus 3 over 2 e to the minus 3t. So this becomes minus 15 e to the minus 3t. And my total response so my total response here has the format k1 e to the minus t plus k2 e to the minus 2t and minus 15 e to the minus 3t. Right? So that's a total response. And then I have to, take my initial conditions into account to solve for initial conditions. So using initial conditions, I get that k1 plus k2 minus 15 has to be equal to 2. And then derivative, so minus k1 minus 2k2 plus 45 is equal to 3. And when you solve, you end up with k1 equal to minus 8 and k2 equal to 25. So your total response is going to be equal to minus 8 e to the minus t plus 25 e to the minus 2t minus 15 e to the minus 3t times dt. So we've solved the same problem that we did in a first example, but much shorter process. Why is there much shorter process? Because we didn't have to do convolution, right? There's no convolution. We have to do convolution for an arbitrary input, but if the input is not an arbitrary, if the input is exponential, then we know a shortcut. The shortcut says that the response to every exponential ends up being exponential. And then you actually piece your final solution not out of the zero input and zero state, but you piece it out of natural modes and steady state modes. Natural modes have to be in the same format as your zero input because they are the natural response of the system. And then the forced modes, they have to be in the form of the exponential that you use for input. Because the linear system excited by the exponential ultimately responds to the exponential. So you piece them together, and then the exponential, you solve the transfer function to get the magnitude and the phase of the exponential. And for the natural modes, you're going to use, they're going to come with some constants here, because you know, all you know is that the system rings with the natural modes, but you don't know what their magnitudes are. And then you will resolve that by using initial conditions. Okay? Let me give you some problems here. So problems associated with this material are 2, 4, 23, 24, 25, 26, 27, 29, 2, 4, 35, 2, 5, 3, so 2, 5, 3, 2, 5, 4, and 2, 5, 5. Okay? So these are the problems. Again, what I said, the next time when you come, we're just going to be doing problems. So just try to solve all the, most of these problems and see where you have some issues, and let's then take them and try to solve them. Okay? That's it.